Hi students. So today we are going to discuss the topic of theory of simple bending. Okay. So the theory of simple bending is defined as nothing but simple bending or pure bending means that there is no shear force in the length of the beam. Okay. And there is constant bending moment. Okay. So here on theory of simple bending it is also called pure bending. Okay. So why we are called it is pure bending means because there is no shear force. So first of all you have to know what is shear force. So what is shear force, can you say me? So shear force is nothing but the sum of vertical forces. Okay, the sum of vertical forces which are moving on a beam. That is just like an example. So this is just like an example. You can see the forces which are there from upwards or downwards. So this will be designated as a negative shear force, and one will be designated as a which are that is sum of upward forces is equal to sum of downward forces is equal, that is nothing but positive shear force. Okay, so then next, what is bending moment? Okay, the bending moment is are nothing defined but the sum of moments which are having in the different directions. Okay, so those are also called in the vertical directions. Okay, so these will be like this. So these are the bending moments which will be there. So this is called sagging movements. Okay, and this will be called as a hogging movement. So here the sagging will be described as a positive and hogging will be described as a negative movement. So this is regarding the bending moment. Okay, so the sum of vertical forces which are equal, that is nothing but shear force, and the sum of moments which are there, that is nothing but bending moment. Okay, so let us see here now. So consider a beam. Okay, so this is the example, a beam is there. You can see the movements which are there. Okay, that is described as m, the movements which are. So this is in the which direction? This is in the clockwise and this is in the anti-clockwise. So left side is clockwise and the right side is anti-clockwise. Okay, so the line which is described, this is known as neutral axis. Okay, so here you can see the example, that is nothing but, so if you consider a small a beam, okay, so a overhanging beam, so describe it is a B C D. Okay, so the two loads are acting same here. Okay, so first of all draw here an SFD for this, how it will be there. So you can see here A B C D described. Okay, so the two loads which are disturbed here, so that is nothing but it considered as a positive and this considered as a negative. So where here the SFD is equal to 0, because where the BC is lies constant, so at the P point it is 0 and at the C point it is 0. So this line where the considered on the BC point is known as 0. And coming to the bending moment, you can see the line drawn here A B C D. Okay, so here the moments will be like this. So this portion is the bending moment, whether it is stated as negative and whether it is stated as positive and negative. Okay, so this is called as BMD. So here also we can see the BC portion which is there, it is in the uniform condition. Okay, so the condition which is satisfied here, so that is there is no shear force in the length of the beam. Okay, so there is in the length of the beam we doesn't have any shear force, so whether positive or negative it will be there, and in the bending moments will be there, but the shear force condition is 0. Okay, so this is for only this condition. Okay, at this type of condition beam only it will be like this. Okay, so coming to here, that is we can write it as a FBC. Okay, so the F is nothing but shear force. Okay, we can write FBC is equal to 0, whether B is 0 and C is 0, so that is written as FBC is equal to 0. And MBC means nothing but movements. Okay, the movements MBC is equal to, it is constant or uniform. So that is nothing but the theory of simple bending is applicable for length BC of the beam. Okay, so the theory of simple bending, it is applicable only in the BC length, because it is states that shear force is 0 So here the theory of simple bending is applicable for the length of the BC of the beam. Okay, and see the next condition, that is, so a beam which is given, so that is nothing but an example. You can see it considered A, B and CD. Okay, an horizontal beam. So here the forces which are there, so you can see the condition, the forces which are acting, okay, so which they act on the beam, so they will be moving in this bending condition. So in this condition it will be acting, the forces will be in the tension, and these forces will be acting in the compression, because when the load falls on here, okay, on the top of the beam, so it will be going down, so then the beam will be changing its length. Okay, the beam will be changing its length. In this length, the whatever the length it is changing, it will be coming near to the neutral axis. Okay, so when it is considered here, you can see that is nothing but it is sigma BD, it is in the tension and it is in the BC compression. Okay, sorry, this is the compression and it is the tension. Okay, so here this portion is known as bending stress. Okay, and this portion you can see here, that is shear stress. Okay, and at the center of the portion we can see, we known as it as tau max. Tau max is nothing but maximum shear stress, where the neutral axis lies within the flange. It is known as sigma shear stress or sigma maximum stress. Okay, so this is the condition. Okay, and these are the fiber points at the corner points. Okay, and at outer fibers of a beam the bending stress are maximum. Okay, and at shear stresses are zero. So these are the outer fibers, A, B, C, D points are the outer fibers. So where here the stresses will be, the bending stresses are maximum, and at the shear force will be zero. Okay, and shear stress are zero, so theory of simple bending can be applied safely for outer fibers. So where the we will apply the, here the condition is nothing but A, B, C, D, the points we can apply the our theory of simple bending condition. Okay, so this states that the simple or pure bending beam, it states the compression and tension in the outer place. So generally if you think this is a beam, okay, so a hinge or whether it is a simply supported beam, okay, so it has given, so whether the load has given at the center point, so this is termed as A and B. Okay, so in this condition the beam will be in the bending condition, so that is nothing but in this condition it will be there. So why? Because when the load falls here, it will be coming at the center of the point, so this center point, it is determines that the point is O. Okay, so this point determines is the point is O, so this beam condition will be in this condition, so it will be in this condition. So it stays here in this condition, so we will be determining like this. So this will be the our center of the neutral axis for the beam, stated as NA. Okay, so where the compression will be there, so in this position it will be in the compression state, and in this position it will be in the tension state, because when the load falls on the center of the point, the bending portion will be getting on. Okay, so here we will state the length which is from the center of the neutral axis at the point O, it is stated that R. So this is known as R. So this R is also called as the our radius of curvature of the beam, so it is determined in the mm. Okay, and this is the neutral axis, and here the O of the point will be determining the angle, so this will be determining the pi or theta. So whatever the angle it will be there in this is a condition. Okay, and some of the examples are also there. So how the bending will be done here, so you can see here a cantilever or simply supported beam. So this is a simply supported beam. So on this simply supported beam, if you see a beam like this, so in this condition, so where the load acts here, so the neutral axis, so here this is known as compression, and here it is known as tension. Okay, so this is SS simply supported beam. Okay, and whereas in the cantilever you can see here, so this is a wall or a column. In this, when the cantilever has there, okay, so the beam which is there here, so it will be coming in like this. So here this will be in the neutral axis position. So where the tension will be there, on the top of the, at the corner of the beam it will be there, and this bottom portion will be in the compression. So why? Because when the load falls on the here on the beam cantilever, it will be the, that means at the edge we will have the compression, but on the nearby at the top of the column or any wall it will be in the tension condition. So nothing but these are the bending stresses. So whatever you are seeing here, these are called bending stresses, and this is the sagging portion, and another one will be in this condition. So this will be in the hogging position, wherever the load which pulls or in the, it takes to the upward force, it is in the hogging. Okay, so this will be negative and this will be positive. Okay, nothing but these are all the stresses which are there in the simple bending. Okay, so let us see now bending equation. So the bending momentum is nothing but here the M is equal to moment acting at the beam, that is Newton per mm. So what is the moment here? So these are the moments. One is acting in the clockwise, one other one acting in the anti-clockwise. So consider a beam. So just like that is nothing but a B, C, D. Okay. So here next one is theta is equal to angle of bending. Okay. So the theta is nothing but it is described here. So that is coming in the our bending portion. And next R is equal to radius of curvature of the beam. So that is described in the mm. So the point from which O2, so the center of the neutral axis, it is determined as R. Okay, so that is nothing but the length of the bending portion at the neutral axis point is known as R. And next you can see here, that is our strain sigma E is determined as delta L by L. You know the formula, stress by strain. Okay, so the strain E is determined as delta L by L, that is known as change in length by original length. Here the condition is the when the length is in the changing condition and original length. Okay, so what is the here delta L by L is nothing means, so this is the actual length. So this is the actual length of the beam. So we are taking the portion that is nothing at the center of the point. Okay, this is the beams is the original condition, whether the load acting or not acting here. The beam is in the constant position, that means it is in the original length. So when the load appears on the beam only, okay, when the load appears on the beam only, it changes its length. So up to what hand it will be changing, it depending upon the load. So let us see here, that is change in length by original length is equal to, so in changing length we have described as PQ. So that is known as, this is the PQ we have determined. This is the considered a one length. Okay, so whatever the length it is changing here, it is considered. So from the bottom of the point it is described as Y. Okay, how much area it is changing the width, that is described as PQ. So the PQ minus P dash Q dash by PQ. So what is P dash Q dash? So whatever the length it is changing, it is described as P dash Q dash. Okay, so before that it is PQ, it is in the original length. Whenever it is changes its length, it is described as P dash Q dash. Okay, so next, that is equal to 1 minus P dash Q dash by PQ. Okay, so 1 minus of P dash Q dash by PQ is equal to 1 minus of, that is R minus Y by theta by R theta. Okay, so here P dash Q dash is described as nothing but, you can see here, that is, so this is P dash Q dash. So this P dash Q dash is nothing but from the point O, that is known as the R, the length up to the neutral axis. Okay, so here R minus, what is the distance from the neutral axis at this point, this is called Y. So R minus Y, that is known as P dash Q dash is equal to R minus Y. So that is known as here p dash q dash is equal to, that is written as r minus y, and this theta is cancelled. Okay, and here is equal to r minus r plus y by r, and r cancel, you will get E is equal to y by r, that is written as y by r. So this y by r can be written as sigma by E is equal to y by r. Okay, so this is in the our strain condition now. Okay, so then it is written as sigma by y is equal to E by r, it is the equation 1. So from this equation, our stress is written as sigma is equal to E by r into y. Okay, so this is our condition. Stress is equal to sigma is equal to E by r into y. So next we have to consider a force on elementary strip. So this is called a strip. So strip means the in the beam the thickness, okay, whatever the in the beam the thickness will be changed. That means the movement in the length, it is called as the strip, and we can call it as also area also. How much strip length it is moving, the width or length, that is known as area. Okay, so here force on elementary strip is equal to sigma into dA. So you can see here, this is the beam. So in this beam, this is the center of the neutral axis, this is the neutral axis, and this is the strip, the moment which is nothing but dA. So the moments m which are there. Okay, so that is nothing but the sigma into dA. Okay, so is equal to E by r into y dA. So what is this sigma? You can see here, stress is equal to sigma is equal to E by r into y, that is written as E by r into y, that is known as dA. So here A is area of the strip, this area of the strip. Okay, and next, so after force the movement will be there. So movement on elementary strip is equal to force into distance. Okay, so that is nothing but dm is equal to E by r into y into y into dA. So what is there here? E by r into y into y into dA. So how it is written here? So the sigma is written here y into dA. So this sigma is nothing but y, that is E by r into y here, E by r into y, and into this y. The y is known as the distance from the strip dA. So dm is equal to E by r into y square, that is dA. Okay, and m is equal to E by r, that is integration of y square dA. So here y square is nothing but I. So we have m is equal to E by r into I. So that is written in the our standard equation, our theory of simple bending equation. M by I is equal to E by r is equal to sigma y